Hello! In our first video lesson, we discussed how PyMAPDL can be used within a web app to bring sophisticated simulation insights into the hands of many people. A basic web app of a mechanical APDL model was described along with a short description of each part of the web app in the third lesson. In the prior video lesson, we concentrated on the backend by changing the example model's PyMAPDL standalone script to one that would work better within a web app along with some other bits. Now, let's finish the web app by completing the front-end parts, starting with the Python file with Flask implementation. Ready? Let's get started. If you have followed along with these lessons on creating a web app, we will start by looking at the app.py file. If you have not followed along or did not make the changes yourself, please take a minute now to download the lessons file package and extract it to a location of your choice. Now, in the app.py, we will keep the run mode in debug, which will allow us to edit the files on the fly if necessary, while still running the web app. Looking at the file, we return a render template from the calculator function. This will essentially present the web page, so first let's look at the page design. HTML, JavaScript, and CSS are well-established standard languages for web development. And while tools exist to automatically generate HTML and CSS files of a page layout, the HTML and CSS files here were written manually. When we started, we had a generic layout planned, but now that we have some additional information, we should go back and look at the layout. In CSS, a grid is defined for positioning the layout, so let's sketch out the layout with a grid. The last row does not need to be equal in size, as it will be the remainder row. The title and reference will be put on the first two rows. The form for inputs, the solve button and model image, will be put on the left-hand side. Then the results table and image on the right. Here, I have taken the grid out and replaced everything with a short description of what the text alignment, color, and background should be. Though we will not cover CSS in detail, let's look at the style.css file included. Here in the title section, the grid position is given with the first row being assumed and columns 1 through 9 used, along with the text being center aligned with a gold background. Now let's move to the HTML file. It starts by giving the location of the CSS style sheet and defining a title, which is the tab name in the browser. Next, within the script section, first the class container is defined. This will point back to the container or grid layout in the CSS style sheet. Similarly, the class title points back to the font and alignment specific given for the title in the CSS style sheet. The input section starts with its own header, which of course, a class pointing back to a CSS style sheet. The input names are then defined as labels, then the values as number input types. The values are saved to variables that we pass back to the Python script. This defines a single line break. These are used as a simple method to group the types of input together. Then the solve button is defined. Scrolling back up, function defines a JavaScript function. Here to change the solve status message and background color to red when the solve button is pressed. Scrolling down here to the output section, we see where the solve status is defined. Similar to the input section, the output section is in three parts of the header, names, and values. Scrolling down to the end of the results section, we see that the JavaScript can be used in enclosed braces to ensure that JavaScript does not conflict with other code. There, a if exists statement is used to determine whether to show the result image, but there is a problem. Can you spot the mistake? Here I have used the total deformation value as a conditional. However, given that the layers thicknesses are the same, there is no dependence on differing Young's modulus, resulting in a different value. And if the coefficient of thermal expansions are the same, the model will not displace in the z direction, but would in the x. A valid solution would not then be presented. We should instead define some condition, here called flag, to use to tell whether the results are available to be shown or not. That was quite a bit of HTML and CSS if this is your first time working with those languages. Moving to the Python file app.py, we will start with the import statements. The module shutil may be new to you. It is a Python module containing functions for working with files. It will be used later to move the result image to the correct location. Let's add importing the constants and pymapdl functions. The import will follow the path to the files with this period style. This imports the whole of the bimetallic file, which is in the folder pymapdl, which itself is in the lib folder of the project. I have also defined the variable images to be the path to the image file folder location using the OS module join function and one of the constants. Moving down to the pymapdl_vm35 function, let's fill that in with the model parameters passed to it. First, the instance of mapdl is launched by calling the bimetallic mymapdl launch in cwd function, given the constant's working directory and job name as inputs. The mapdl instance and a variable holding the full working directory path is returned. Next, the processing of the model is done by calling the bimetallic solvevm35 function, which all the parameters, mapdl instance name, and image path as inputs, returning the path to the result image and the value of the maximum z deflection. These are in turn returned from the pymapdl vm35 function with an additional operation of rounding the maximum z displacements to 3 digits. Moving on to the calculator function, which defines the values used in the HTML file, we first need to define all the default input parameter values. That is done, and you will notice there are a few here that are not in the model input parameters. We have defined as empty to initialize a variable for the usum, which will hold the maximum z displacement. Image is the path to the image file. Works zmax is the value returned from the reference calculation. Error1 will hold the percent error between the pymapdl and works value of z displacement. And flag will be used to determine when results are ready to be presented on the web page. That is complete, so let's move down to the post method. This will request the values from the web page and then use these in the function call to run the model's pymapdl script. The return variable prun is a list. A message can then be printed to the terminal window, which launched the web app, to alert that the run is complete. Printing to the terminal can be a useful debugging tool. Next, the first item in the prun list, as place 0, is the result image file. The shutil function move is used to move this file to the static folder with the file name used in the HTML file. The solve complete flag used in the HTML file is set to 1 or true, and usum sent to the second item of prun, the maximum z displacement amount. These can then be printed to the terminal window as well. Next, we call the reference calculation works zmax. The percent error between it and the pymapdl file will be reported, but a 0 z displacement will give a divide by 0 error, so we need to work around this as a 0 is a valid value. An if-else construct is used to define the percent error to be 0 if the absolute value of the displacement is not greater than 0. Otherwise, calculate and return the percent error. With the calculation complete, the function can now return the Flask render template function with all the variable values used in the HTML page. Let's fill that in. That's kind of a long list, so one value per line is used, aligned with the first value. This makes the return easier to read. Save our work, and we are ready to run the web app. If you have been following along in Visual Studio Code, click the Run button in the upper right, then in the terminal window, control-click the URL. Your default browser should open a new tab and show this. Try a few values of the inputs. If a mistake has been made and the web app does not run, and you cannot find the mistake, you can download the lesson's final files package. Before we finish, let's take a minute to step back and review the web app. Running app.py is our web server. Opening a web browser and going to this URL triggers the calculator function with the HTTP method of get, meaning get some data from the server to show. The data are the default values, which are then used by the HTML file to render the web page. Looking at the HTML file, if the solve button is submitted or clicked, then the HTTP method changes to post. Some JavaScript is used to change the state to solving with a red background. Post sends data from the web page back to the server. Back to the server app.py here, if the if statement, when the method is post, the various inputs get their values from the web page form. Then the function call is made to py_VM35, which in turn calls two functions in the bimetallic.py file. These create or clear out the working directory as needed, start up the mapdl instance, then process the pymapdl model and return the results. The mapdl instance is then shut down. The result image file is moved to its proper location and the single value result obtained. Here we really should rename the result as it is z and not total displacement, but this will be left to you to try. The variable flag is set to be used by JavaScript in the HTML file to know when to show the results. The works closed form solution retrieved and the error percentage calculated. This data is then sent back to the HTML file and the web page rendered with the results. Phew, that's it. This concludes the video, and I hope that you have found these lessons informative and useful. Happy learning!